Hi everyone, my name is Dongwon Lee. I want to first thank the organizers for hosting such a great workshop. I am really excited to present our work on cross-modal clustered contrastive learning, grounding of spoken language to gesture. And this was a joint work with Chaitanya Ahuja and Louis-Philippe Morency. I want to start off this presentation by showing you two gestures. Consider the following two gestures, gesture A and gesture B. Do the gestures look similar? But at the same time, can we really assume that the speaker is saying the same phrase? Well, here's the answer.
The Milky Way forward, the Milky Way forward, until today, until today.
From this example, we see that similar gestures can be mapped to very different phrases. Formed refers to a scientific phenomenon, and today refers to a point in time. However, their accompanying gestures are very similar. Therefore, we see that the same gesture can accompany semantically different spoken language phrases. Given that the same gesture sequence that co-occurs with semantically different spoken language, the embedding space may not capture the similarities in the gesture space. Therefore, this many-to-one relationship requires going beyond conventional losses that focus solely on a reconstruction quantity to learn cross-modal grounding. We introduced the cross-modal cluster noise contrastive estimation, or CCNCE, to learn a gesture-aware embedding space where the similarities and dissimilarities in the gesture expressions are taken into account when learning language embeddings. We use this gesture-aware embeddings for the downstream task of gesture generation. Our approach involves two main steps. Given a sequence of gestures, we cluster the gestures in a self-supervised way. We find aligned language embeddings. And with our cross-modal cluster NCE loss, we coerce the aligned language embeddings, which may be semantically different, to be closer together if they belong in the same gesture cluster, and far apart if they belong in different clusters. I will first explain gesture-based clustering. In order to find similar gestures, we first estimate the global mean and variance of pairwise gesture similarity. Given two arbitrary pose sequences yi and yj, we find the mean and variance of the pairwise dot product. These estimates are used to find a threshold, which is used to determine whether two sequences are similar or not. For example, sequence yi is considered to be similar to sequence yj if their dot product is greater than mu plus k times sigma, where k is a hyperparameter. With this thresholding logic, we construct a global dictionary of clusters of poses, and we align the corresponding language embeddings as well. Each cluster should have Ci number of similar gesture sequences with corresponding language embeddings. We refer the audience to the paper for a more detailed explanation. Given a new anchor point Z and Y, we compare the global dictionary of clusters with the same thresholding logic. We find the most gesture-wise similar cluster in the global dictionary. With a constructed cluster, we properly assign positives and negatives for contrastive learning. And with our cross-modal cluster NCE loss, we coerce the aligned semantically different language embeddings to be closer together if they belong in the same gesture cluster, and far apart if they belong in different clusters. I will explain more in detail about this now. Contrast learning requires three elements: an anchor point, positive samples, and negative samples. The main idea is to construct an embedding space where the positive samples are close to the anchor point, and the negative samples are far away from the anchor point. Our work draws inspiration from Joshua Robinson's work examining that hard negative mining improves performance, and also from MoCA, where large batch sizes with a large number of negative samples are drawn. Our method differs in the way that positives and negative samples are drawn. From the cross-modal clustering, we are able to find the most gesture-wise similar cluster in the global dictionary. We use a corresponding language embeddings of the most similar global cluster as positive samples Z+. The negative samples are drawn from language embedding sequences in the other clusters in the global dictionary. With this assignment, we utilize the properly assigned samples in our cross-modal cluster NCE. The numerator encourages us semantically different language representations to be close together since they belong in the same gesture cluster. So, given an anchor sequence Z and the gesture-wise similar positive language embeddings Z+, and their dissimilar negative Z-, we feed these language embeddings into an encoder, which we denote as F, to learn the relationships in the gesture space. By doing so, the cross-modal cluster NC guides the language embedding space to learn the similarities in the gesture domain. We have described the full approach, where gesture-based clustering helps assign proper positives and negatives, which is used in the CCNCE to learn a gesture-aware embedding space. Finally, this is jointly optimized with the reconstruction and adversarial loss as in previous works. The heat map is an actual overlay of gesture sequences that were clustered together using our self-supervised clustering algorithm, which demonstrates intra-cluster similarity and inter-cluster dissimilarity of gestures. The heat map plot demonstrates that the self-supervised clustered pose sequences are indeed similar. Each row of the heat map displays an overlay of 3 individual 64-frame sequences in a specific cluster. For cluster 7, the gesture is dominated by a raised right arm and an up and down motion of the left arm. For cluster 9, the speaker is at their rest pose with slight up and down movements of the right arm. For cluster 6, we can see that the left arm is mainly static with movements on the right arm. Visually, we can see that cluster 6 and 9 are actually quite similar, with movements mainly dominated by the right arm, whereas cluster 7 is quite different. The right is an actual TSNE plot of language embeddings before our CCNC loss was applied. We see that similar gestures occupy different regions in the embedding space. The embedding space has little to no information about the similarity between gestures. Now, after applying our CCNC loss, we find a gesture-aware language embedding space, where similar gestures occupy similar regions in the embedding space. We also see that clusters 6 and 9 lie closer in regions in the TSNE plot of the language representations in comparison to that of cluster 7. This demonstrates that the intra-cluster and inter-cluster relationships are preserved in the gesture-aware latent space as well. From these TSNE plots, we can easily see that our CCNC loss was effective at guiding the representations to be aware of the similarities and dissimilarities of gestures. If the clustering information was not effectively transferred to the latent space, we would not be able to visually see the clusters in the TSNE plot located in similar regions for the gesture-aware encoding. We utilize the multimodal, multi-scale transformer-based GAN architecture as the primary building block of our proposed model, which is ours without CCNCE in gray. We compare our model with other contrastive learning approaches, MoCo and Patchwise, by replacing the loss function from CCNCE. MoCo is indicated in orange and Patchwise is indicated in blue. For L1 scores, lower is better. Our proposed model with the inclusion of CCNCE produces better L1 scores than other baselines. We see a significant decrease in L1 scores, and this implies that our CCNC model produces better well-timed and relevant gestures compared to other baselines. Specifically, we see that other contrastive learning approaches, L-MoCo and L-Patchwise, have worse L1 scores than that of the baseline model without any contrastive learning. This additionally shows that our proposed method of constructing clusters in the output domain and coercing the model to learn a gesture-aware embedding space is beneficial. Although our results show improvement in precision, we see that our model having worse FID scores, which represents the coverage of the generated distribution. The node contrastive learning method, which uses an adaptive importance sampling approach for better performance and coverage, produces the best results. We are providing additional incentive for the model to generate a limited subset of gestures, as we are mapping a large language space to a smaller subspace of gestures. Therefore, a decrease in the FID scores is explained by the trade-off between precision and coverage. In our work, we studied cross-modal grounding in the context of many-to-one mapping between spoken language and gestures for the task of co-speech gesture generation. We introduced a new contrastive loss function, cross-modal cluster NCE loss, which guides the latent space to learn the similarities and dissimilarities in the constructed clusters in the gesture domain. Furthermore, we offered a mechanism to cluster temporal sequences in a self-supervised fashion. We demonstrate the effectiveness of this approach on the PATS dataset, which indicated that our proposed methodologies outperform prior approaches in grounding gesture to language. We also observed that encouraging higher precision could potentially degrade the coverage of the generated gestures. To conclude, I want to show you a good cherry-pick sample from our model.
436 kilojoules, I get 2 moles of hydrogen atoms. So 2 moles, twice the standard enthalpy of formation of hydrogen. So I find a relationship between the tables, their strengths and weaknesses of each method of calculating enthalpies for chemical reactions. The strength here is, let me remember just a small number of things and be able to calculate
Thank you, and I would love to take any questions or receive feedback.
$436 kilojoules, I get 2 moles of hydrogen atoms. So 2 moles, twice the standard enthalpy of formation of hydrogen. So I find a relationship between the tables, their strengths and weaknesses of each method of calculating enthalpies for chemical reactions. The strength here is, let me remember just a small number of things and be able to calculate